The birth of Optimus Gen 3 didn't occur on an assembly line or in a sterile laboratory, but within a vision repeated by Elon Musk over the years. The creation of machines that don't replace people, but coexist with them. This premise, once distant, underwent a radical change in 2025, when the project ceased to be a futuristic demonstration and became a large-scale corporate movement. And as happens in every technological revolution, the starting point wasn't a finished product, but the courage to pursue a concept previously considered impractical. Now, what was once a dream is getting closer and closer to concrete reality. When Musk presented his goal to engineers and directors in March 2025, the atmosphere was filled with a sense of unease. He spoke of producing thousands of Optimus units that year, something that seemed excessively ambitious even by Tesla's standards. For 2026, he projected 50,000 units, and in 2027, 500,000. These numbers were received with astonishment and even some skepticism, natural reactions to any technological leap of this magnitude. But if there's one thing history has taught us, it's that Tesla thrives precisely where others hesitate. Shortly after, however, came the setback that unexpectedly put the project in jeopardy. Leaked internal reports indicated that Optimus production had been paused due to unavoidable technical bottlenecks. The largely manual assembly made any industrial scale comparable to that of electric vehicles unfeasible. The dream of an army of humanoid robots suddenly seemed distant, like a promise too premature. But following the Tesla pattern, the pause did not mean defeat. It meant reorganization and profound redesign. In the following months, subtle signs began to emerge behind the scenes at the company's factories. Employees reported anomalous movements, unexpected meetings, and restricted areas being expanded. In July, it became evident that something was being reborn within the project. Tesla had resumed production, but this time quietly, with units intended exclusively for internal use. These were robots being tested in the environment where they could learn fastest, the company's own assembly lines. Then came the announcement that changed the course of the narrative. Tesla confirmed that a new wave of robots was rolling off the assembly line at a rate of over 1,000 units per month. Each one represented the next evolutionary stage of the project, the highly anticipated Optimus Gen 3. There were no exuberant presentations, no brilliant demonstration videos. There were only numbers, objective statements, and the absolute confidence that the world would witness a structural transformation. It was the typical silence that precedes disruptive advances. According to Musk, the third-generation Optimus represented the first version truly aligned with the company's original concept. It was no longer a prototype struggling to find its balance or an experiment moving towards refinement. It was a product with solid engineering, designed to be scalable without compromising performance. Musk even stated that there were no significant flaws remaining, a rare comment from someone known for seeing imperfections even in the impossible. Now, all that remained was to scale it. Over time, internal information began to leak, revealing details that fueled global curiosity. Optimus Gen 3 had not only improved, it had been reinvented. It was lighter, more efficient, smarter, and above all, more capable. With approximately 3,000 integrated tasks, its versatility easily surpassed that of the 2.5 generation, which already impressed with little more than half of that. For comparison, most current industrial robots don't even perform 100 distinct functions. Among these 3,000 tasks, examples emerged that went beyond the industrial field. The robot could fold clothes, transport heavy boxes, inspect automotive parts, organize stock, and perform delicate actions, such as cracking an egg without damaging it and preparing simple meals. This wide range of capabilities demonstrated not only programming, but also advanced motor learning. Each gesture was the result of a neural system inspired by the model used in Tesla's self-driving cars, now translated into the body of a humanoid. This philosophy of shared intelligence became the backbone of the project. Elon Musk has always argued that if a car can navigate chaotic roads, a robot can navigate everyday human life. Both require quick decisions, movement predictions, and complex environmental interpretations. The same visual architecture that drives vehicles now guides a bipedal body, analyzing distances, objects, and behavioral patterns with fluidity. It's not just engineering, it's neural adaptation applied to movement. The evolution of robotic mobility depends directly on what are called degrees of freedom. Each articulation point is an axis of movement, an extension of motor capacity. Version 2.5 already had 22 degrees of freedom in the hands alone. Version 3 expanded this even further, increasing precision, sensitivity, and fine manipulation capabilities. With each additional axis, Optimus gets closer to human behavior, not only in appearance, but also in operational biomechanics. The robot's design also received special attention, with Musk describing it as elegant. This elegance wasn't limited to the visual aspect. It was a concept rooted in physical efficiency. Every servo, every metal plate, every sensor was positioned according to principles of balance and mechanical fluidity. The result was a human silhouette that evoked familiarity rather than threat, an intentional contrast to avoid associations with aggressive futuristic figures. It's worth remembering that it wasn't always this way. The world initially reacted with disbelief when the Optimus concept was presented at AI Day 2021. The initial version was nothing more than a statue, followed by a presentation with a costumed actor. The internet ridiculed the idea, calling the project a distraction, but year after year, functional prototypes began to emerge, gaining form, mobility, and purpose. The journey from disbelief to respect was long but consistent. Now rumors suggest that Tesla is preparing the first public unveiling of Optimus Gen 3 at its annual shareholder meeting, scheduled for November 2025. Internal sources suggest that the event could include a live demonstration with several robots operating completely autonomously on stage. If it happens, it will be a historic audio-visual milestone, the first public presentation of a group of humanoids operating without direct manual control. More than just an aesthetic redesign, the Gen 3 promises significant advancements in human interface. One of the most talked about new features is the integrated front display, capable of showing relevant data such as battery level, tasks in progress, and information captured in real time. Furthermore, the robot will be able to respond via voice, using the Grok system, allowing for natural, direct, and extremely dynamic communication. Internally, the robot was redesigned piece by piece. Motors, actuators, cameras, and sensors underwent in-house development processes that completely abandoned off-the-shelf commercial solutions. Tesla concluded that no available industrial component met the precision and durability requirements demanded by the project. The result was a brand new hardware chain, produced from scratch to seamlessly integrate with the company's robotic intelligence. This intelligence, in turn, shares the same infrastructure used in the full self-driving program. Optimus doesn't just learn through programming, it observes, reproduces, and evolves. Simulation plays a key role, allowing the robot to virtually experience millions of scenarios before executing them in the physical world. Each unit in real operation feeds data back to the system, accelerating collective learning. It's a distributed neural network with a mechanical purpose. The scale of this collaborative learning surpasses any previous benchmark. Imagine thousands of robots performing simultaneous tasks, all connected to a large equivalent digital brain. Every motor adjustment, every error corrected, and every interaction is recorded and processed by the network, which redistributes the improvements. In this way, the whole system evolves as an artificial species, a constantly mutating digital organism guided by physics, code, and statistics. Despite the excitement, challenges remain. Humanoid robots face problems that conventional machines don't have to solve. Balance, for example, is a sensitive equation influenced by terrain, weight, posture, and even micro-vibrations in the motors. Stairs, wet surfaces, or irregular objects add complexity. Each failure is potentially catastrophic, requiring fast and highly anticipatory correction algorithms. Tesla knows this, and that's why it maintained absolute secrecy about most of the tests. It wasn't just about perfecting hardware, it was about developing natural behaviors, the pause time before an action, the fine-tuning of posture when initiating a movement, and the way the robot avoids obstacles are as important as the power of its motors. The goal is for the behavior to appear intuitive to the human eye. Within gigafactories, test units are playing a crucial role. Robots are already performing simple tasks such as transporting parts, inspecting machines, and providing logistical support. Employees working alongside them report that autonomy is increasing rapidly. Unlike traditional industrial robots, Optimus does not follow rigid routines. It interprets the environment, makes decisions, and understands patterns based on real-time visual indicators. Meanwhile, Tesla reached a historic agreement with Samsung Electronics for the production of AI-6 chips, a key component in the advancement of humanoid robotics. With a joint investment of approximately $16.5 billion, production will be concentrated in Taylor, Texas. These chips will not be exclusive to autonomous cars. They will form the cognitive basis of Optimus, enabling processing speeds never before applied to a bipedal robot. This level of vertical integration completely transforms the economic landscape of the project. While other manufacturers rely on multiple suppliers, Tesla seeks to build virtually everything in-house: hardware, software, motors, sensors, chips, and AI systems. This degree of control reduces costs, accelerates development, and creates a self-reinforcing internal ecosystem. It's not just engineering, it's industrial strategy. The initial price estimate is also impressive. Musk suggested that Optimus Gen 3 could hit the market for around $10,990, a surprisingly low price for a humanoid capable of replacing entire fractions of the workforce. If confirmed, this would not only democratize access to advanced robotics, but would also pressure the entire global technology market to adapt to a new paradigm of personal automation. Skeptics argue that such figures are impractical or exaggerated. But these arguments echo criticisms previously leveled at the Model S, the Model 3, and SpaceX's reusable rockets. On all these occasions, the general consensus was that Musk overpromised, and yet repeatedly his improbable proposals have become reality, not by magic, but by his insistence on breaking traditional industry cycles. If Optimus achieves its scaling goal, the social impact will be profound. It is estimated that Tesla could reach a production of 1 million robots per year by the end of the decade. This would represent one of the greatest redistributions of the workforce in the modern era. Entire factories could operate with hybrid teams of humans and humanoids, and ordinary families could rely on domestic robots for the first time. This advancement also opens up important ethical debates. The replacement of repetitive tasks by machines can be seen as liberating for the worker, who would leave behind exhausting functions to assume creative or supervisory roles. On the other hand, there are concerns about how entire economies will absorb the transition. Researchers warn that public policies will need to keep pace with the speed of technology to avoid social disruption. Internally, Tesla engineers describe the project as the creation of a new species. This phrase, at first glance exaggerated, reveals an essential principle. Optimus is evolving through iterative selection. Each version corrects flaws, expands capabilities, and adjusts behaviors. Unlike conventional products, evolution occurs not only between generations, but within them, thanks to continuous learning. Musk himself often compares the current moment to the beginning of the Model S development. At that time, Tesla faced severe criticism and widespread disbelief. Now, reliving that challenging environment, the company is once again venturing into uncharted territory. But this time, the product is not a car. It's a new type of worker, a versatile assistant, a physical agent of artificial intelligence in the real world. At the heart of this advancement is the Dojo supercomputer, responsible for training the neural networks that power both autonomous cars and humanoid robots. Dojo was originally designed to interpret traffic scenarios, but its generalization capabilities made it ideal for teaching body movement. The robot's intelligence doesn't come from linear instructions, but from simulated and real experiences accumulated over millions of iterations. Training at the dojo allows Optimus to learn motor skills with remarkable efficiency. Instead of relying solely on static algorithms, the robot develops emergent behaviors, enhanced by the accumulation of data from the entire fleet. This process causes the system to evolve in a manner similar to an organism in constant learning, refining gestures, response time, and accuracy based on patterns detected by the AI. The ability to observe, repeat, and improve makes Optimus especially efficient in dynamic environments. In a factory, it can learn from mistakes, adapt to process changes, and even identify operational improvements that humans would hardly notice. The robot doesn't just follow instructions, it interprets context and makes decisions consistent with its programming and collective neural training. Another fascinating aspect is how Optimus interacts with its surrounding environment. Proximity sensors, depth cameras, and spatial mapping systems allow the robot to understand the three-dimensional world with remarkable sensitivity. This includes detecting minute variations in the floor, anticipating collisions, and automatically adjusting its posture, maintaining fluid locomotion similar to that of a human. Locomotion represents one of the greatest challenges in robotics. Walking on two legs requires balance, weight distribution, trajectory calculation, and anticipation of falls. Each step of the Optimus Gen 3 is the result of hundreds of simultaneous microprocessors, all synchronized in real time.